Welcome to example number 12. We have a marathon stair climb. So we have a Chicago marathon runner who's running up a set of stairs. She has a mass of 50 kilograms. And she's running up this Willis Tower, the tallest building in Chicago. It has a height of 443 meters. And she does this in a time of 15 minutes. So we're asked to find out what is her average power, and we want to know what it is in watts and kilowatts and in horsepower. And then we're wondering if the runner's work output was collected and sold at a rate of 10 cents per kilowatt, what would be the cash value of her work? Okay, so to calculate the average power, it's the rate of doing work. So it's W divided by time. Now, I suppose you could go about and find the force that she's exerting upwards. I assume that she's moving up these stairs at a constant velocity, so her kinetic energy isn't changing. And really what she's just changing is in gravitational potential energy. So you could use the force that she applies upwards, which would be equal to her weight, and multiply by the height. That would be one way to do it. So you could use force multiplied by displacement, multiplied by the cosine of the angle between the force and the displacement, which would be 0 degrees, and divide by time. But I think maybe a better way to do it is to think that the work done is equal to a change in gravitational potential energy, which is potential energy here, and that's equivalent to mgh over the time. It's probably the fastest way of solving it. So our average power would be 50 kilograms multiplied by 9.8 meters per second squared, then multiplied by the height of the building, 443 meters, and then divided by the time that it takes her. Now remember, we want our power to be in joules per second. So we need to change that 15 minutes to seconds, and there are 60 seconds in 1 minute. This gives you an average power of 241.2 joules per second, which is really 241.2 watts. So we've got the first one written in watts. If you need to convert from watts to kilowatts, 241.2 watts, we would multiply by 1 kilowatt all over 1,000 watts, because that's what 1 kilowatt is equivalent to, and the watts would cancel out, and so when you divide by 1,000, you're going to get 0.241 kilowatts. I guess we'll just change this, just get rid of the 2 here, and just write everything in 3 sig figs. If you want to convert to horsepower, let's go to our 241 watts. We know in 1 horsepower there is 746 watts, and so that will give you an answer of 0.323 horsepower. Okay, that's for part A. So now part B, we're looking at what would be the total cash value for her work done. Now, the work is equal to the potential energy, and the potential energy would be just mgh. And so that mass again was 50 kilograms times 9.8 meters per second squared times the height of 443 meters. And so this gives you an answer of 217070 joules. And I guess I probably should have just taken my power, by the way. That would have been better. It's 241.2 or whatever it was joules per second. And then multiplied by our time. That would have gave our work. That would have been another way to do it. I should have done it that way. Or 15 minutes is 15 times 60 to get that in seconds. Anyhow, well, we got the work in joules, but we know that the price is the price in kilowatt hours. So the price that's given is 10 cents for every kilowatt hour. So we're going to need to convert those joules into kilowatt hours. And you remember, if you recall, 1 kilowatt hour is equivalent to 1,000 watts, which is a joule per second, multiplied by an hour, which is 3,600 seconds, and the seconds cancel out. So it's really equal to 3.3 million 600,000 joules. So let's convert that now. So if we multiply by 1 kilowatt hour and then divide by 3,600,000 joules, we get the work, the energy that was transferred while she was running the marathon of 0.0603 kilowatt hours. So then our total cash value would be, well, the price is 10 cents for every kilowatt hour. And so if we multiply by how many kilowatt hours we have, then we get 0.00603 dollars, which is basically not even a cent, 0.6 cents. And that's it for example number 12.